By far, the most widely cited proof for relative motion is the Michelson Morley experiment. In this experiment, an interferometer is used to try to measure Earth's motion in space. This is a simplified version of the interferometer. Light entering in the lower left corner is split into two beams. They travel more or less an equal distance, L, and are reflected back to the origin to be combined, and form an interference pattern. This short animation shows the path taken by two photons as they travel the length of the two arms. The time that it takes for a photon to make a round trip is derived from these equations. L equals v times t. That means that t equals L over v. In this case, v is the speed of light. When the interferometer is in motion with a velocity of vm, then the path that light follows is longer and takes a longer time. For the vertical arm, a full round trip, tv, is given by this formula. For the horizontal arm, th, the formula has two components, for the left to right and right to left trips. With a little algebra, we get these equations. For Vm greater than 0, the time on the vertical arm will always be less than the time on the horizontal arm. When the interferometer is rotated, then the interference pattern will change as the two arms trade places. The Michelson Morley experiment had arms with the length L of 11 meters, with enough sensitivity to measure Earth's orbital speed around the Sun. Michelson and Morley were not able to detect any motion at all. They got a null result. This experiment has been repeated numerous times with identical results as seen in this chart. The null result is cited to validate relativity's premise that light is constant for all frames of reference. We'll come back to revisit this experiment and others later on and propose a different explanation for the result.